Well, thank you all for joining my session, and thank you so much for our Stir Track organizers for putting on this conference today. I am super excited to be here. I'm an Ohio State graduate, and this is my first time presenting in Columbus. And I feel like I've really come full circle in my career. My first role, the first people who took a chance on me after deciding I should switch careers was at JP Morgan here in Polaris. Big shout out to that team for taking a chance on me when I didn't know how to use an Android device, let alone program for it. So they're the real MVPs here. With that, a quick introduction. My name is Sierra. I'm a senior software engineer at Twitter and a Google developer expert for Android. And this is my favorite talk to give because I am not an expert in this subject and also have never used it professionally. And so I like to really set the bar low as we get started, knowing that I completely made all this up and have no idea what I'm talking about. Every year, Google, or at least most years, puts on an Android Developer Google Challenge. Last year, they did Jetpack Compose, the new framework for Android development. And 2 years ago, they did ML for Social Good, where Android developers put together applications using ML-Kit to solve social good problems. There were really cool applications that came out of that. One for recognizing the number on the bottom of the recycling things and then finding somewhere close to you where you could recycle those items. There were a lot that monitored your heart rate and did other things with your health to find trends and those sorts of things. And when this was happening, I was super overwhelmed by all of these folks who were Android developers, and I was an Android developer, and had no idea how to do that. And it gave me a lot of imposter syndrome around that, where I'm like, I have this skill set, all of these folks are also Android developers, but how can they do machine learning? And so this talk came from that imposter syndrome. And so today, we're going to kind of start from that same place that I was starting from, and we'll just grow up on that personal project and personal journey where I learned ML-Kit from scratch. ML-Kit is one of my favorite packages that I've explored, and from my experience, it's very approachable for the average developer like myself. And so I'm really excited to share it with you and get started, including experimenting with all of its different fun features. So with that, let's go ahead and dive in. If you are interested in these slides or the material or the application that we're going to build throughout this presentation, it is available online, bit.ly/stirtrash-ml-kit, or through this QR code. And that will be displayed again at the end. So feel free to check this out and play with it on your own time as well. So let's get started with what is ML-Kit. I think some of it's given away with the name. But ML-Kit brings Google's machine learning expertise to mobile developers in a powerful and easy-to-use package. Some things to think about with ML-Kit is, number one, it's optimized for mobile. It offers real-time on-device processing, which makes it unlock use cases like using processing camera input, and also works offline. So if you're looking at images or any kind of data that needs to stay on your device, you can do that with ML-Kit without ever taking that data to external server. It's also built by Google, which means you can take advantage of the machine learning technologies that power Google's own experiences on mobile. But I think that the more important takeaway in this particular case is that it's already built and you can get started using it. And finally, it is easy to use. And so you can tell me after this presentation whether or not you agree with that assertion from Google's documentation. So what can ML-Kit do? ML-Kit is broken into two different subsets. First, the vision APIs, and then also the natural learning APIs. With our vision learning APIs, we can see a lot of different things that we can do to process images. We have things like facial detection, segment augmentation, if you want to build your own Snapchat. We can do barcode scanning to build a Kroger competitor, object tracking, pose detection, digital ink recognition, text recognition, and image labeling. On the natural language API to things, we also have language ID. They can tell you what language you're looking at. You can do things like entity extraction. So if you have an app with messaging and you want those messages that say, hey, let's meet at Stir Trek on today's date at 7:30 a.m., you can pull that out and put it on your calendar. We have Smart Reply if you want to include those very awkward recommended LinkedIn messages when people reach out. And you also have on-device translation, so you can look at the things in different languages and immediately translate it to something that you understand. And so you can see that this ML kit is really going to open the door for you to build really powerful and customized applications. In addition to that, everyone can use it. It's going to be available for both Android and iOS. So beyond being a very exciting and fun thing to use in my personal projects, but it also means that in the production environment, you can also take advantage of this because it's going to give you parity between the two major platforms. Both your iOS and Android kits can pull in the ML kit dependency and have the same sets of data and same models, giving you about the same output. Additional to this, for our cross-platform enthusiasts, it is also available for Flutter projects as well. So with that, let's meet our client for the next hour or so. This is our client, Steve. Important things to know about Steve. Number one, he's my dad. And this is Steve and his famed tractor. He's quite proud of this tractor. And as it turns out, my mom and my dad are a great tag team, where my mom buys a lot of plants and my dad plants a lot of plants. And so he has this problem where he's planting all these plants for my mom, and he doesn't always know where they are, what they are, but he does finally understand what I do, and he figured that out. And so he asked us if we can write him an app to help with this problem. And so with machine learning, the ML kit, the answer to that is yes. We're going to use the image labeling vision API to help Steve identify his plants in real time. So let's go ahead and get started. So before we actually get started with the ML kit, I want to make sure that we're all on the same page with knowing what to expect in all the different words with Android development. I mentioned that ML kit is available for both iOS and Android, but as an Android expert, we're going to lean down that native Android path. And so today, we'll be writing a native Android code using Kotlin, and all of our code will be in one activity. So some of the words to take away from this is that native Android just means that it's going to be specifically written on the Android operating system. And the Android operating system is open source, and so Android or a modified version of Android is actually running in a lot of surprising places, like a Kindle and your refrigerator. Kotlin is an object-oriented language from JetBrains, and it's going to remind you a lot of Java, but more concise and less boilerplate. Notably, I am thinking about older Java because Android has never been updated past Java 11. In 2019, Android became a Kotlin-first platform, and I am, for one, a huge fan of Kotlin. We could spend an entire talk talking about how powerful and all the different use cases and how to use Kotlin, but today we're just going to be sticking to the basics. And then finally, all of our code is going to live in a single file, and that's going to be our main activity. If you're familiar with Java, then you know that there's a special main function that's going to start everything up. And that's kind of how you can think about the activity in an Android application. It's going to orchestrate all of our UI and all the functionality associated with that. And so this is what we're going to get started building. So it's a simple single-screen app, our activity. And we're going to be using a constraint layout to lay out our different UI elements. There's not much architecture to our app at all beyond separating up into different functions. And again, all this code is available if you want to dig deeper into the specifics. But here's just the rundown of what to expect. We have this constraint layout, and that lets us constrain different UI elements relative to each other in our UI. And then we just have this background preview image. It's going to be an image view to display what image we're looking at. We'll have a recycler view to display the labels. And a recycler view is just Android's version of a list. And then we also are just going to have some buttons to make it really easy to navigate this application. So one to select an image and one to process that image. In Android, we use Gradle to manage our dependencies, and so there's two different ways that you can add the image labeling dependency into your project. The first way that we have here is going to bundle the model into our application. The second option is that we can also dynamically download that model from the Google Play services, and you have two different options with that as well. You can either download it immediately when they install the application, or if this is a feature that may not be often used in your application, you can choose to download it on demand when they're using that feature. In the second way, it's going to make our app a little bit smaller, but it also depends on network availability. And so that's something that you want to think about when you're deciding how to implement this in your application. Since we're building this for Steve, and he's going to be using it out in the yard, and my parents are notoriously frugal and do not have unlimited data plan, we're just going to go ahead and download that, add that right into the app, build it into it, so that it's definitely going to be there when he needs it. We're also going to be using the base model today. Steve is a great client. He understands the importance of an MVP and iterating on that. And so this base model has 400 different labels that we can just use out of the box. It's just available for us as part of MLKit. The model is meant to be very general and a varied list of words that's going to have some kind of impact no matter what you're kind of looking at. And so this is just a sampling of the words available in this particular model. So we have things like bird, jersey, dragon, goggles, flowers, airplane, bench. And so you can go and look at this full list of options that are going to be built into that base model. And we'll get started with that and see how that works for us. All right, so Steve takes and sends a lot of pictures to our family Snapchat, and he will also screenshot everything you send him as well. So I know that he has a lot of pictures on his phone to work with. And so again, in this first simple implementation, we're going to let him select a photo from his library and then analyze it in the app. And so that means we first need to let Steve pick an image from his photos, and then we'll need to take that URI and transform it into a bitmap. And so to do this with Android, we're first going to use this function, start activity for result. And what this function does is let us open another activity or application in this particular instance, and then expect data back from that. We're going to use an intent, which is an abstract description of an operation to perform. And in this case, we set that type to image and the action to get content. And so these combined together say that we're going to go out, pick an image, and come back to our application. And when we come back, we call this other function on activity result. And when that request went OK, so we get this result OK, then we can pull that data out. And so that's how we get our image URI. And then we're going to jump into this set preview function, passing in that data. And so with this set preview function, then we're going to transform our image URI from the activity result into a bitmap using the bitmap factory. And so here we see that we're just going to open that URI, use the bitmap factory, and then return an image. And for good measure, just to make our UI make sense, we're also going to use that bitmap to set the preview image. And now it's time to jump into some of that MLKit. So we now have our bitmap, and we can now convert that into an image input that the image labeler is going to need. Here we have image input.from bitmap, and we're passing in our image bitmap and also 0. 0 is going to represent the angle, the rotation angle, and so we can either pass in 0, 90, 180, or 270. It's worth noting that there are other functions here that we could use beyond from bitmap. There's also a direct from URI. We chose to use from bitmap because a bitmap with the 0 angle rotation is actually going to be the most efficient. And we also need that bitmap to set our preview anyway, so we would have been doing that work regardless. Next, we're going to set up our image labeler. And so we have our image labeling.get client, and we're going to pass in default options. We also have options to set specific parameters and constraints on the data that we want back from our image labeler. For example, we can say we only want images that we're very confident are going to be in this image that we're processing, so we can set a confidence layer level inside those options instead. And so then we've created our on-device image labeler. And so we can pull these things together. We have our image input, we have our labeler, and so we call labeler.process, pass in our image input, and then we wait. So this particular function is going to return a task that returns in the future asynchronously when it's done processing. And so in order to get those results when it's done, either successfully or as a failure, we add an on-success listener and also an on-failure listener. And so when our images processing is successful, then we get back a list of labels. And so we can do whatever we want with those labels. In our case, we know where we're trying to end up with. We're trying to add those into this recycler view. And to just bridge between that data, that recycler view, we're going to set up an adapter and then pass in that list of labels. Each one of those labels is going to have a text. And since we're using the base model, this text is going to match the labels, one of the labels that we saw in that base model. It's also going to have a confidence to represent how confident this process was in that this label is in fact in our image. And then it will also have an index, which will just be an integer. And this actually maps back to those 400 as well. So really the text and the index are going to be telling us the same thing in two different ways. And so for this simple example, we just bind together these different values to row views in our cell, and we're good to go. And so now we can go ahead and try that out. So our app is loading. We're going to go and select an image, actual image of Steve's backyard, and we can go ahead and process that. And so we get back things like petal, trunk, jungle, forest, garden. And so we see that our model recognized things that could relate to what we expected, things like flowers, plants, and gardens. It's also worth noting that Steve would be absolutely thrilled that Google has some confidence that his backyard is a forest or a jungle. And so where are we going to go from here? While it was really cool, and Steve would be really excited that Google labeled his yard a jungle, the base model probably isn't specific enough for our app, and Steve might actually want us to build a custom model so that he can use this in his yard on the actual plant he's working with. And so we can do that using TensorFlow Lite. Using custom models is going to give us a lot of the same benefits of MLKit. It's very easy to use. It has a lot of the similarities to what we've already seen, the same type of APIs. It also handles the label mapping for you by extracting the labels from the TensorFlow Lite model. And then you can also have choices like to host that model on Firebase so that you don't have to package it with your app. So again, if we think back to how we pulled this dependency in, we have those same kind of options using a custom model. Now, before we jump into this, let me quickly remind you what I am not. I am a mobile developer, and I can answer all of your deep and pressing questions about Android development, but I am not a machine learning expert, and this is not meant to be a deep dive into TensorFlow, transfer learning, or these things that we're going to talk about in the next few slides. These are things that I learned about when I was putting together in different pieces that I toyed around with, and so I'm just going to be telling you what I know about them, but I'm sure that there are experts even here at this conference today who can give you much more depth answers about what these different things do and why you might want to change these different things. And so with that, let's do it. Okay, so how do we get started with custom models and MLKit? The docs for custom models with MLKit tell us that there are 4 different ways to get started with creating custom models. We can use TensorFlow Hub, TensorFlow, AutoML Vision Edge, and TensorFlow Lite Model Maker. Let's look at some of the differences between these different options, and then we can decide which one is best for us. So let's get started with TensorFlow Hub. I like to think of TensorFlow Hub as kind of like GitHub for TensorFlow models. There's a lot of creators out there who have already created TensorFlow models and have put those out into the world so that you can also use them, so that you can just snag instead of building your own. It's going to offer a wide range of pre-trained image classification models from other creators that you can search and filter and pick a model that is MLKit compatible and download that TensorFlow Lite file, and then you're pretty much immediately ready to go. The criteria for finding something that is MLKit compatible is going to include an input that is exactly one tensor, and the data in that has to be RGB pixel format. That makes sense. We're looking at images. The data also has to be in int8 or float32 type, and the tensor is a 4-dimensional tensor, which is going to be batch, by height, by width, by channels, where that channel also has to be 3. Batch is also going to be the number of images that you use for one iteration of your model training, and for MLKit, we're actually going to be limited to 1. And then our output tensor for something that's going to be MLKit compatible is either going to be a 2 or 4-dimensional tensor. The reason that we're talking about this now is because we're going to see this pop back up a little bit later in this talk, so now you're ready for it. To be fair, though, going out to TensorFlow Hub, great option to get started, but we're really looking to build our own model, and so this will just be pulling someone else's. So let's look at some of the other options. We can also use TensorFlow and convert a TensorFlow model to a TensorFlow Lite model. This could be really useful if you already have that TensorFlow model that's created and you're using it somewhere else, and you just want to port that over into a mobile application. So you're already running it somewhere, and you want that to be portable on your phone, ready to go any other time. This converter is available from TensorFlow.org, and you can do it using relatively simple Python APIs. I unfortunately do not have a TensorFlow model that I'm going to be able to use, so again, we're going to go ahead and skip this option. The next choice we have is going to be the AutoML Vision Edge. And image classification models that are trained using AutoML Vision Edge are supported by custom models in the image labeling MLKit APIs. These APIs are also support download of those models and can be hosted again with that Firebase model deployment. The basic steps for using AutoML Vision Edge is you're going to just copy a whole data set of images into Google Cloud Storages, and then you're going to create a spreadsheet listing the image and their associated labels. Using AutoML Vision Edge, you can then create your data set, train a custom AutoML Vision Edge model, and then make a prediction. And after you're happy with all of that, you can export that and deploy your AutoML Edge model and use that in your mobile application. However, cloud services financially scare me. I cannot risk my financial future by accidentally setting something wrong in GCP. And so I'm going to move on to the next option. And yeah, okay. So finally, you can also use a TensorFlow Lite Model Maker library. This model maker is going to retrain a model, which is also known as transfer learning, and takes less time and less data than training a model from scratch. During training, an image classification model is fed images and their associated labels. Each label is going to be the name of a distinct concept or type or class that the model is then going to learn to recognize. Right now, it supports several use cases and is not limited just to image labeling, which is what we're going to be doing today. But we can do image classification, text classification, gesture recognition, and many others. And so it gives you a lot of flexibility, a great place to start regardless of what your use case is. And so today, we're going to be using this model maker, and this model maker that we're specifically using in this presentation is going to be available online through the link in this slide set. We're going to be using a collab for this image classification with TensorFlow Lite Model Maker, and that's going to take us step by step through building our own model. So if we were to jump out to that model maker link, the model maker is just a Python notebook that's going to guide us through the process of building a custom TensorFlow Lite model. If you've never worked with Python or these types of notebooks, that's totally fine. I generally do not either. You don't need to know much about either to use this step-by-step model maker. This notebook is just an interactive computational environment, and it's going to allow us to run each line of code separately in this virtual environment, which I'm told is very important for Python development. The first 2 lines that we see here of executable code are just going to get your environment up and ready so that we can go through and build our own model. The first step is a pip install of a bunch of required packages. Pip is a package manager. Some of the things that you're going to install in this particular collab is going to be some of the TensorFlow packages, like TensorFlow, TensorFlow Lite, TensorFlow Lite support, TensorFlow JS, and then you'll also need some math packages as well so that we can do a math plot later on in this collab. You can find the full list of things that it's going to install and add to your environment by going to the repo that's linked in the model maker. Now that those packages are available to us, this second line is just going to import the important things into our actual notebook. It just so happens that Google actually has a very large flower data set that is of images publicly available that we can use to get started building Steve's plant identification application. And so the first thing that we're going to do is go and grab all those images from Google Cloud Storage, so I didn't get away from Google Cloud Storage. This get file function just takes a file name, the origin, which expects in a URL. In this case, because these flower images are a tar folder, we need to set extract equal to true and pass that in just so it knows to untar this folder. And this is just a utility which is part of the TensorFlow core. Once we have that data available, then we can run through the next couple of steps. The first step is going to be using the image classifier data loader class to load our data in, and we just load it from that image path that we just talked about in the last slide. When we do this, we actually get a lot of information about what that data looks like, and so we see here in this info that we have tensor load image with size, and so we learn that that particular data set has 3,670 images. And we also have 5 different labels. Those labels are going to be daisy, dandelion, roses, sunflowers, and tulips. The next thing that we're going to do is take this data that we've just pulled in, and we're going to split it up into training data and then the test data. And so we'll split that using a 90-10 split. With that training data, we're then going to use our image classifier.create. We're going to pass in all that training data, which is going to create our custom image classifier model from our training data. The next step in this, after we've done this, is it's going to let us check the loss and accuracy of our model. And so we pass in our test data into our model.evaluate, which will tell us the loss and accuracy. We remember that this test data is already labeled, and so it knows what the answer should be, and so it can compare that to what it gets back using the model that it just created in the step above. And when we're happy with the loss and accuracy and think it's a viable model, then we can go ahead and export that, and we're basically ready to go, which also seems pretty easy. I want to take a step back and talk about this image classifier.create function. This is going to be the critical part of this entire collab and this entire library, because this is where we use transfer learning with pre-trained model to create our own custom model. Thankfully, almost all of that is hidden under the surface. We don't actually have to know anything about it if we don't want to. But I do want to talk through some of the different options that you have here and kind of what it does, so that you know things that you can change and tweak if you're making your own models. This is also the slide I rewrite every single time I give this talk, because I can never get it quite right. Again, speaking from my mobile background on what transfer learning is. So what's going to happen here? We have this pre-trained model, which is a saved network that has been previously trained on a very large data set, and then we can customize it to our particular use case using transfer learning. The intuition behind this idea of transfer learning for image classification is that this pre-trained model that we're going to use is very large and can give us a general idea of what the entire world, the entire visual world is like. And then we can use those feature maps to map our own model instead of starting completely from scratch. The default trained model that we will use by default with this image classifier.create is the efficient net light 0. But there's, again, a lot of different models that we can use, and that's one of the arguments that we can pass into this create function. Some of those other model options are the mobile net light v2, ResNet 50, and there's actually 5 different efficient net light models that we could also use. So we're using 0, but there's also 1, 2, 3, and 4. Each of those efficient net light models is just going to vary in the number of trainable parameters that they have. And if you don't know what trainable parameters are going to be the weights that can be updated or optimized during each training iteration or gradient. A really example of training parameters is if you think about a random set of data that you wanted to model with a linear line. Linear line is y equals mx plus b. And so the 2 training models that we have there are the m, so the slope of the line, and also b, the intercept of that line, so that we can best fit that data. And this is just going to be on a much larger scale. It turns out that the efficient net light models are going to be a really good choice for us because they're a set of mobile-friendly image classification models. They're developed by Google and need less computations and parameters to classify images. They're built to be small and fast, and if you compare the models to one of these mobile net or ResNet, they're going to have better trade-offs between accuracy and size and latency. But again, you can switch between them in this particular function and to find which one works the best for your data. When I switch between the efficient net light and the mobile net, the accuracy of this particular model dropped from about 93% down to about 86%. The create function is going to download this image feature vector from TensorFlow Hub. So we didn't get out of using TensorFlow Hub either. And the image feature vector is just a dense 1D tensor that represents the whole image. It's just going to be a list of numbers used to represent it. Inside this function, it's going to split that data again into training, validation, test data, and testing data according to the parameters that you can also specify in this function. And by default, we're going to take 80% is going to be the training data, and then 10% validation data, and 10% test data. It's really hard to talk while hearing this echo. This is a new experience. I haven't talked in person in a while. And so what's going to happen after that is we're going to add a new classifier head with a dropout layer. And that dropout layer is going to help us fix overfitting. What the dropout layer is going to do is randomly set things to 0 throughout that so that it doesn't overfit. And so if you think about a model trying to fit to the best accuracy, it's going to be some kind of bell curve. And so we want to hit that peak. And overfitting is when you go past that peak and continue to try to fit further, but you start decreasing your accuracy. What it's going to do is going to pre-process that raw data that we put in. Those steps are going to include normalizing the values. So we're passing in images, and so each of those pixels is going to be a number between 0 and 255. The efficient net light need that input data to be between 0 and 1, so it's just going to normalize that down. And it's also going to take whatever size it was before and normalize it to the size that the efficient net light model needs. And so that's going to end up being 224 by 224 by 3 channels, which again is going to map to the RGB. And then finally, it's going to feed all that data into that classifier model. And then by default, we have a lot of different parameters we can again tweak and update to find the best fit for our model. Some of those different things that we can change are the epoch. The epoch is a full training pass over the entire data set, such that each sample has been seen once. By default, that's going to be set to 5. And more epochs could, again, achieve better accuracy, but eventually converges on that bell curve and can lead to overfitting. So it's something that you can tweak, but as you start to see that accuracy fall, you're now overfitting your data with too many epochs. You can also In this particular crate, you can update the batch size. We are again limited by ML kit. We need that batch size to be 1, but the batch size is going to be the number of samples to use in one training step. We can adjust the learning rate. The learning rate is going to say how aggressively this model should adjust when it sees new things, how quickly it should override the things that it's already learned. So if we were doing something with like roses and we passed in all red roses and it suddenly sees the purple, is how quickly should it overwrite the fact that it thinks a rose should be red? And then there's other things we can change, like the momentum, which helps you optimize as well. And so all of these things I recommend if you're going through this code lab to tweak them and see how they're going to affect your data set. Once you've tweaked them and again you're happy with your model, then you can move on to that next step and export your data and start adding it to your application. And so that's the step we're on. So we're happy with our model. We've created this custom model to look at different flowers, and so now we want to add it to our Android application. And so we can do this. If you're in your Android application, you'll have an application package. And so we can open that up, add something new, and you can see that at the very bottom of this list, there's an other, after all the things that it usually expects you to add to Android apps, and we can add a new TensorFlow Lite model. And we click on that, we're going to be launched into a wizard to help us integrate this into our application. We go out, we find where we download this TensorFlow Lite model. We also have options to add specific Gradle dependencies so that we're best prepared to start handling this as soon as we've added to our application. When we do this and we push finish, we're going to be dropped onto this new screen that's going to model after adding the model to our project. When you see this, it's going to tell you a human-readable way to learn things about your particular model. We'll jump back to this in just a moment, but first we want to look at the other things that it's changed about our particular project. So if we look at the diff of our project after adding this TensorFlow Lite model, there's a few different things that we see. First, there's a new package in your package structure. Normally with an Android application, you're going to have your Java package that's going to hold all your data in logic and all your Kotlin code. We'll also have a resource folder to hold things like images, layouts, strings, and these sorts of things. A manifest to orchestrate our whole application, and now we will also have an ML package added to that. And inside that is going to be our lone ML TensorLite model. We can also see in our build Gradle that we've updated those with new dependencies and build features. We noticed that the ML model binding is going to go inside the same chunk of code called build features, and that's just going to give us ways to build our app better. Other things that would go in here include our view binding, data binding. If in current Android, this is where you would enable compose as well. And so it's just going to make it easier for us to directly import those TensorFlow Lite model files and then use them in our project. And then we also pulled in two new dependencies, the TensorFlow Lite support, which is a cross-platform library that helps us to deploy TensorFlow Lite models onto mobile devices. And then finally, the TensorFlow Lite metadata library that includes both human and machine readable information about what the model is and how to use that model. And so having talked about that, we can return to this screen that explains what our model is. And this is that visualization of the model, the metadata that is human readable like we just talked about. So there's a few things we probably want to note about this. First, we see at the top that we use the efficient NetLite model. It's also automatically given us a description. It's stolen our credit and says that TensorFlow is the author of this beautiful model that we're using. And then if we look at this input and output tensor, we should recognize a lot of those numbers from earlier in the talk. We recall that the criteria for input was RGB format, data in the 8 or 32 float type, and a 4-dimensional tensor batch by height, by width, by channels, and that channel is 3. And so what we see here in our particular input is that we do have float 32 and our input image to be classified. That shape is 224 by 224, which matches back to the efficient NetLite size that we talked about, and then a batch size of 3. And our output is going to be a 2D tensor with the shape 1 by 5, and those 5 represent the 5 labels that we have in this model, respectively. And so now we can use this custom model in our application, and so we see that it's really similar to what we already have. So instead of creating an input image, we're now going to create a tensor image. Again, we'll just use that bitmap that we've already set up to pull from the image, from our image library. And so we'll do tensor image.fromBitmap and pass in our bitmap. We now need to create a new instance of our model, so we'll do flower model. Mine was named flower model.new instance. And then similar to before, we have flower model.process. We pass in that TensorFlow image. And what's going to come back out is a list of probabilities, and they have some really nice utility functions so that we can make them easier to display. And so we can map those from those probabilities into a list of categories. And then in this case, I'm going to go ahead and sort it by how likely it was that label. Then we use the exact same function to set up our recycler view, pass that into the adapter, and we'll be able to see that in our list by binding that into those rows. Categories versus our labels that we saw before only have two different attributes. So they're going to have both the label, which will be the label. It will come from that list of data that we passed in. And then the score is the same thing as the confidence that we had prior. And so with that, we can now try this out as well. So this time we'll select an image of a sunflower and run our new model. And so we get back that sunflowers with a 96% confidence. We can try the same thing with our original image. And so if we select an image this time, same one as before, process that image, we get back some confidence, but very, very low in comparison. Roses at 50%, tulips at 42%. But the key takeaway here is we do have a custom model. It can identify 5 different flowers: daisies, dandelions, roses, sunflowers, and tulips. But what happens if we want to categorize Steve's favorite flower, his pride and joy, the Kana's flower? And since we're machine learning experts now, we should be able to do this. So if we download that package that we use of flowers that we use to create this first custom model and open it up locally, we see exactly what explained what it should expect. So we have this top-level flower photos, and inside we're going to have 5 subdirectories, and those subdirectories represent our different labels. So we have the dandelions, daisies, and so on. And each one inside of each of those different folders, we're going to have a lot of images. And so it becomes really obvious how we can add a new flower to our model. We can go ahead and add a new subdirectory, the Kanas, and then add a bunch of pictures. So the next thing that we need is a bunch of pictures of this Kanas plant. There's a lot of tools online available to help you scrape the web and get all those pictures very quickly if you want to do that. But a few things that we want to know is, number one, we need a lot of pictures, and we're going to need them from different angles. In the case of Kanas, where there's different kinds, we see the purple leaves, green leaves. We want to encapsulate all those in our different data sets. So we don't want them all to look exactly the same. So it's more likely to be able to identify a Kanas no matter what angle we're looking at or which variation that we're looking at. It also only supports JPEGs or PNGs, so we want to make sure that we pull those images only. And at minimum, you need at least 32 images to add this to your model. For comparison, remembering that the other data set had over 3,000, each one of those folders had about 700 images inside them. And so I've downloaded all my images. We want to add it to our model. We're going to basically run through the exact same steps. We can go back out to our Colab. On the right side, there's an option to just upload your own instead of reaching out to that URL. So we can upload this new folder. I uploaded a zip of those flowers with the Kanas included, and then just update that URL and run through the exact same thing. Again, have any kind of options to tweak, but when I'm happy, then I have my new, add it to my Android project the same way, and I can go ahead and try it out using a picture of Kanas from Steve's backyard. So when we play this one, we'll select this picture that he so proudly sent to me. We'll process that, and we get back Kanas again at 47%. So you may immediately ask me, why is that so low in comparison when we did the sunflowers where it was at almost 96%? Number one, Steve's not here. I'll throw him under the bus. He has this bad habit of zooming in on pictures instead of just like walking forward, so almost all of his pictures are a little blurry. Number two, I want to really push the limit of how many pictures I could add to get a meaningful result. And so this one only had about 45 pictures of kanas added to the model. And when you think about that in comparison to these other folders that have 700 photos, and we were able to get a 47% confidence that this is the correct flower. And so if we continue to add more kanas in his, we would only continue to see that number increase. So where do we want to go from here? We have now created a custom data model. We know how to scale that out. We know how to add all the flowers to create a really robust flower model if we wanted to do that. And so the next thing that we could consider doing is maybe using the camera. That's one of the use cases that MLKit specifically calls out, is that we can use this for use cases that want to use real-time data input, so that I don't have to go through the process of selecting an image, uploading that into the application, and so forth. So let's look at what that looks like. So this actually turns out to be a very frustrating Android-heavy process that you need to know a lot about life cycles and cameras and all this different things that we do not have time to go into today. But I think the pseudocode kind of reads for itself to know where we're going. So what you'll need to do is you need to add new dependencies to your application. We know how to do that. We add those to our Gradle. So we need dependencies for camera X. We need that for camera X lifecycle. And we also need a special view to display that image proxy as we pull in that real-time camera input. Because we're good at application developers, we'll also ask all of our users if it's okay, if we can use their camera. So we'll need to add that to our manifest as a permission to ask for. And then we'll also need to add some code in the activity to actually process that. And so what that's going to look like is we're going to use the process camera provider and the image analysis classes to bind our camera to our activity and build an image analyzer that's going to convert these image proxies into a bitmap. And then we know what should happen once we have that bitmap, pass it into our process function of our model, and then display it in our recycler view. And we can also display it in that preview view, the preview view that we've done every single time as well. I realize that there's a lot happening in this sentence, and so this is completed on the branch MLKit-camera out on those materials on GitHub. High level look at what this is actually going to look like is we have this camera provider future. And anything with future means it's going to happen sometime in the future, and that almost always means we're going to add some kind of listener to listen to those changes. This is where we're going to create our image analyzer. And so we can see, again, a couple numbers that we recognize. We're going to set our target resolution to 224 by 224. That's been the number throughout these different models. We're going to use a back pressure strategy to keep only the latest so that we're always looking at the most current picture from our real-time camera. And then we're going to use this image analysis to actually analyze our different images. And when those outputs come back, we can display those in our UI. Some of the other things that we have to think about, we'll set our camera to the back default. We don't need to process our faces, looking for flowers. And we have to deal with our activities to make sure everything's aligned. And then we also have to set our previews somewhere along the way. Our image analyzer is going to look like code we already know and recognize. So we have this analyzer, and we get that image proxy from our real-time camera. And then from that image proxy, we can do a bunch of image manipulation, again, things outside the scope of this talk, to convert it to our bitmap. And then once we have that bitmap, we're good to go. We can create our TensorFlow image, we can create our model, we can process, we can make that a category list, we can sort it by descending, and we can hand that back to our display. And so with that, let's go ahead and try out this code. And so we see here our outputs updating as we move from flower to flower on the camera versus selecting an image instead. All right, so where do we go from here? We have now made our custom data model. We now set up our camera to load an image. The next thing that we might want to do is overlay that image with labels so it's really obvious what we're looking at. This is actually done in the Google Sample app for ML Kit, which I think is a little overwhelming the first time you look at it. But now that you've set through this, you have a really good basis going into that to find that functionality if you're interested. I am personally very excited for Jetpack Compose on Android, so we could scrap this whole app and rewrite it in Jetpack Compose. It should all be supported. And then finally, last but not least, and also the hardest, I have to convince my dad to use an Android phone so they can actually use this application that we built. And so with that, my last reminder to all of you here, and aligned with our Star Trek theme, I think they've showed Spider-Man in the past, is with great power comes great responsibility. I'd be absolutely remiss not to end on this note when we're talking about ML and learning. We are not building these models, right? We're using transfer learning. We're building on top of someone else's model that has already been trained. And we need to always be mindful of any kind of basis that's going to be learned in, that's going to be baked into any kind of learned model, and the potential harm and impact that it might have on our users. We're doing something kind of silly here, but we know that ML can have real impacts on people in the world. And so with that, thank you so much for sitting through this presentation. Again, you can find all of this code online on GitHub. My GitHub is just OBryan. If you want to find me, you can find me online, _OBryan on Twitter, or OBryan.dev has all of my contact information as well. And with that, I think we have some time for questions, and Steve in front of his kanas. No questions.
Did you ever get the model to update live with your camera feed going over things as you get it? Did you ever try confirmation, like live updates?
The question was, have I used the model with camera input?
Yeah, like with live updates. Like, have you tried it?
Oh, the actual model live updating? I have not tried that. I have always included the model built into the application and not tried to add on that additional learning factor. Yes?
So it was individually in the camera picking out individual objects. Does it have the possibility of, like, you show it a room and it gives you the possibility of what is the chances that a couch, a chair, a lamp, like, would it give you percentages of what it thinks those objects are in the room, or is it just very specific? It gives you, like, it hones in on that one object?
It will try to, the question was, can you pick out multiple objects at the same time? It will try to pick the most prominent object in the image. So as you scan the room, you'll see different things, and there would be options, for example, like to scan the whole room and save off those different highest percentages. And then you could display, okay, this is the full image of this room that I've moved through in some like graph, like grid-like way. And so this is everything that's probably in this room, for example. All right, well, thank you all so much.